Check, 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 mic check. Check, 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 mic check. All right, good day, what it do? This is Dr. Drew. And we're gonna do an impromptu live stream. And today, I wanna go over reactions of aromatic compounds. Let's see how many we can do in one go. Reactions of aromatic compounds. Unfortunately, I'm not going to take any questions right now unless people ask me some really concise questions, but I don't have any in the Discord, so today I'm going to take the opportunity of doing some reactions of aromatic compounds. You guys cannot see that. All right. So probably have to zoom out just a bit, just like this. Fix this, close that. Fix this, and move it over just like this. All right, so today we're going to do reactions of aromatic compounds. And so I'm going to basically just do a bunch of mechanisms because that's the thing that a lot of students are struggling with. All right, so the first mechanism we're going to do is electrophilic aromatic bromination. Bromination. Hi Jake. Hi Djan, Chris. Hello everyone. Guys, my name is Dr. Drew. Welcome into the chat. Okay. Hi Johan. Hi Rainbow Ron. We have electrophilic aromatic bromination is going to be a mechanism that you're going to encounter in organic chemistry. So anyone taking organic chemistry, let me know. So this occurs when we have effectively, let's say, a benzene, okay, or halogenation here of a benzene ring. First things first, I'm going to do a sort of, let's call this like a pre-reaction. We're going to have bromine, Br gas. This is Br2 in the gas state. Hi, Dan. And we're going to react with FeBr3. Okay. So we're going to effectively attack this Fe and create a sort of complex. So complex is just simply like, it's just like they're attached to each other. That's all a complex is. They're kind of like attached to each other. Hey Toss, hey Too Saucy. Welcome in. What's up, what's up? Just doing a little quick impromptu live stream because you know, I had a free hour. I was like, hey, might as well hop on live. I'm going to be back later today to answer questions. I might not take questions right now. I just want to record some quick little mechanisms because this is not my usual time. Yeah, just a little impromptu. Can you do isomerism? Hey, Owais, can you come back later today? Owais, can you come back later today? What time is it for you? Right now it's 2 o'clock for me. I'm going to be back at 5 o'clock to answer questions. I'm going to do aromatic bromination right now. By the way, what about isomerism is confusing for you? What part of isomerism do you need help with? It's 10 o'clock here? Okay. That means it's going to be late for you, so. All right, here's what we're going to do always, because you're probably not going to be able to make the live stream. It's going to be 1 a.m. when I start, so let me finish this one mechanism and then record a clip, and then I'm going to do isomerism in like 5-10 minutes. Sounds good? So bromine combines with FeBr3 to form this complex. We're just going to call it Br plus FeBr3 minus. Okay. And then what we're going to do is we're basically going to take our benzene ring and react it with this complex. So benzene is going to look like this. Let me move this to the side. Benzene is going to look like this. And remember, benzene has the word ene in the suffix here. So ene means it's going to have our double bonds. So let me draw these enes. 1, 2, 3. And so I'm going to react it with the complex that we just generated. Br plus FeBr3. What's up, everyone? Welcome in. Thank you for the love. Jeffrey, welcome in. Okay. So our benzene here is going to proceed and attack this compound over here and move over that bond, just like that. Okay, we're just doing a little quick little live right now. I'm going to take questions later this afternoon, but anyone that's just joining into the chat, welcome in, guys. I'm Dr. Drew. And so we're going to generate our first resonance structure. Again, this is called electrophilic aromatic bromination. A lot of people have been asking about these benzene reactions lately. I thought we'd go over it one at a time. I'm gonna create this. So one of these double bonds is now gone, and we attacked the bromine is now attacked here. Okay, so this is called the arenium ion. Oh, Wise, thank you for the follow. And hopefully I'm saying your name correctly. Okay, so I do have a resonance structure here. So who knows how to do resonance? Mathematic Fanatic, good to see you. Lewis, welcome in. Kaylin, Beep Boop, welcome in. So this is my positive charge, and it lives right over here. Oops, I drew this wrong. There's got to be a double bond on this side. Perfect, just like that and like that. There we go. So if I want to do resonance, that means I got to move my double bond to facilitate that charge transfer, meaning that got to be a double bond right over here. Bromine doesn't move, and I have a positive charge here. I'm triggered. And next we're going to do one more structure. I'm going to go this way. And I'm going to... Oh, almost forgot this one. Okay. And then now I'm going to facilitate that motion through this double bond. Shia, welcome in. Esnile, welcome in. Guys, how's it going? I'm Dr. Drew. Just doing some mechanisms here. And then finally, I'm going to generate my third and final resonance structure. All right. So all of these are quite equally stable, so nothing much we can do here. But now, notice that my bromine is right next to my cation. So in fact, I'm actually going to go back over here, okay, and interact that with my remaining complex. Technically, we don't need to show the rest of these resonance structures, but I'm going to react that with my FeBr3, which remember we generated from this step. So this F minus is going to now sort of we're going to do some proton transfer here. So this proton is going to be attacked by this bromine. Okay, and then we're going to recreate a double bond this way. So I'm going to erase that for our resonance structures and show that here. All right, perfect. So let me know if you guys can see that. I think we're still good here. Let me just shift this over to the side. All right, and then so what we're going to have now is we effectively generated our benzene attached to a bromine, and that is going to be our product. So this is the product for our first reaction here. This is called electrophilic aromatic bromination. Why proton transfer? Because bromine here is going to act as a Lewis base. We have a lone pair of electrons. And this proton here, that's a great question. This proton here is readily acceptable to be attacked here. That's a great question, Shaki. All right, so quick starting example here, reaction here. A lot of people have been asking me about these aromatic reactions. Okay. And oh, Wise, let me know if you're still here, my friend, because then you're going to be up next for that first question here. And guys, anyone that's new in the chat, welcome in. I'm Dr. Drew, going over some aromatic bromination here, electrophilic addition of bromine onto the benzene reaction. And guys, I'm live every single week, Monday through Thursday. And if anyone has any questions, feel free to drop them down below. I can help out with OChem math, Gen Chem physics. So, Wise, let me know if you're still here, my friend, because you had a question about, what was that? Resonance or structures? Let's go back. Thank you for sharing the live. Thank you for tapping the screens. We already hit 1K likes. Just drawing the structures, isomerism. So let's do a quick poll, guys. Do we want to continue with aromatics or isomerism? So I'm going to do a quick poll. Isomerism versus aromatics. And guys, let's just see the vibes. If you want to switch gears here to isomerism, vote for a happy face emoji. If you want to do aromatics, that's supposed to be a crying emoji, chat. So let me pull up the poll real quick. Okay, Elias is here, so thank you for getting back to me. Give me 1 sec to pull up the poll. So in a second, it's going to come up on your screen, I think. And perfect, 60 seconds on the clock, starting now. If you want to switch gears here to isomerism, please vote happy face. And then if you want to do crying emoji, that's going to be for aromatics, continuing aromatics. Be able to work out all possible structure formula from organic when given molecular formula. All right, you got it, Elias. You got it. All right, so we're gonna do some examples for isomerism. And again, guys, I go live Monday through Thursday. I usually go live a little bit later, so if you want to come back later, that's fine too. But yeah, guys, we're gonna do isomerism. And let's start with some simple ones. So some general isomers we can go through. And barely hitting functional groups. Oh, interesting. Guys, whoever's taking OChem, comment down below. Are you taking OChem right now? Say me. Are you taking organic chemistry right now? Say me. If you've already taken this class, don't say me. And if you're taking organic chemistry right now, tell me if you're taking organic chemistry 1 or organic chemistry 2. So the first one I want to give you, I already have some examples up on my YouTube channel. So like, for example, I want to give you, let me see if I can just do it from memory. Studying for the MCAT. So that's not a problem. You can always review. Beep boop. So let's start off with like N-pentane. Let's start off with N-butane. Okay. So for N-butane, you do have to memorize a couple things, chat. The suffix but means 4. Meth, eth, prop, but. This is going to be 4 carbons. This is a suffix for 4 carbon chain, right? So I'm going to draw my carbon here, and then I'm going to draw 1, 2, 3, 4. Okay? So this is the bond line structure of N-butane. And if I draw these H's here, again, I have videos on this on my channel, so just look right if you want to rewatch this. Or just sub to my YouTube channel. It's the same as my name here, Dr. Andrew Sanchez. Just look up Dr. Drew Engineering Minds if you want to watch this on my YouTube channel. The video, I think, is called Isomers or something like that. Alright, so this is the same as this, right? Because we have 1, 2, 3, 4. And each of those junction points is 1 carbon. So let's define the chemical formula here. We have C4, and then how many H's do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. So this is a branch chain alkane. So branch chain alkane means that it looks like a tree trunk, or it looks like a tree or a stem. And so this is the longest chain here. Longest chain. And the C4 indicates that it's N-butane. But we have some isomers. What do I mean by isomers? I mean that we're going to have another compound that has the same formula, C4H10, but it's going to look like a little bit different. So does anyone know what that's going to look like? Comment down below if you know what our first isomer is going to be for C4H10. Hi Red Luna, good to see you. So comment down below if you know what the C4H10 isomer is going to look like. We're going to have our isobutane. So this one was N-butane, okay? But we're also going to have isobutane. So isobutane, guess what? It still has the same formula, right? C4H10. But it's going to have a different branching. So what do I mean by branching? I'm going to have my 1, 2, 3, 4. And it's going to take a little bit of creativity. Okay? Carbon on the second chain. So that's right. I'm going to have a carbon just like that. So this is called isobutane. Let's just make sure that this is the same compound by drawing out the bonds and the atoms. with our carbon here. For instance, carbon bonded to carbon, carbon, carbon. Now each of these on the sides here are going to have 3. Why are they going to have 3? Someone comment down below why each of these have 3. And this one is also going to have 1. So this compound over here on the left is the same exact compound here on the right. It's just a little bit more defined out here. This is C4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the same thing, right? That's C4H10. Is that making sense? So someone asked why. So these have 3 on the side here because of the octet rule. Carbon that is sp3, meaning single bonds only. sp3 means single bonds. Chat, if you're confused about sp2 versus sp3, sp3 means single bonds. So all of these carbons are sp3 hybridized. And so therefore they require 4 bonds to each carbon. So these carbons on the side here are already occupied by 1 carbon, meaning we have 3 left to have a total of 4 per carbon. 1, 2, 3, 4. 1, 2, 3, 4. Is this making sense? Chat, do me a favor, comment down a thumbs up emoji if you're following along and this is making sense so far. If you're on kinetics, you're not cooked. If you're on kinetics, you're not cooked. I got you on kinetics too. Chat, do me a favor, drop a thumbs up if that made sense. If you're confused still, drop a crying emoji. So we're going to take it one step further. I want to do N-pentane. Guys, how are we doing here? Drop a thumbs up. Let's see some thumbs up or some crying emojis so I know if I'm going too fast or too slow. So pentane is easier because pent, it sounds like pentagon. So how many carbons does pentane have? If butane stands for 4 and pentane sounds like pentagon, how many carbons does pentane have? Comment down below. Guys, thank you for the love. What is homologous? Oh, wait a sec. Chat, I'm sorry. I missed all these comments. It's kind of paused. Are we still live? Okay, there we go. We got some thumbs up. There we go. Apple juice. No, I keep calling you apple juice. It just looks like an apple juice box. Or it's like a shopping bag. I called you apple juice last time because I can't tell what that is. The person that has that green, it's like a green, what is that emoji, chat? Okay, I'm gonna say apple juice box. OY said 5, Beep Boop said 5, Snoopy, crying emoji. Snoopy, what part is confusing for you, Snoopy? Snoopy, where did I lose you? Shakira says 5, 5, 5. Melly says 5. Beautiful. So pentane means 5. So I'm gonna draw N-pentane, and I'm gonna draw 1, 2, 3, 4, 5. You're gonna say, wait a sec, Andrew, that's 4. 1, 2, 3, 4. That's only 4 lines. I'm not talking about the lines, chat. I'm talking about the carbons. 1, 2, 3, 4, 5. So at each of these points where I highlighted, that's 5 carbons, right? And thank you for the follow. So this is N-pentane. Let's draw it out, what it's gonna look like. So that's gonna be carbon bonded to carbon 5 times. Do you see how now that's 5? Pent means 5, kind of like a pentagon. So then I'm going to have 1, 2, 3 on this side. And then 1, 2, 3 on this side. Carbon that is sp3 hybridized that is not bonded to any other carbons, namely a methyl group, is always going to be CH3. What about the ones in the middle? I know it's going to be how many here in the middle? I know it's going to be 2. You say, Drew, how do you know it's 2? Because I told you we need to have sp3 hybridized 4 total bonds. Carbon has 1, 2, 3, 4. Carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4 bonds. This carbon has 1, 2, 3, 4 bonds. Am I going too fast, chat? Let me know if I'm going too fast. So this carbon has 1, 2, 3, 4. So all of these carbons are sp3 hybridized. Chat, comment down below sp3. Comment down below sp3. Everyone say sp3, chat. I want you to lock it in your brain memories so that way you don't forget. sp3 means that we're single bonded to 4 different R constituents. Okay, Mac, thank you for the follow. Snoopy, thank you for the follow. Good. Cat said sp3. So the more you repeat it, the more you teach someone else, you're gonna lock it in your memory. Narcy, good to see you. Narcy, you're a chem major, right? Good. Shakira said sp3. Good job, everyone. Good job. So this is N-pentane. Let's see what is the formula. So someone comment down below the formula for N-pentane down below. I'll give you a hint. It's of the form CXH something. HY. So I'm gonna give you guys a couple minutes. Congrats, Narcy. Guys, we're going over organic chemistry right now, and then our friend Narcy down in the chat just finished his degree in chemistry, so congrats on that. I think. Did you finish chem? Oh wait, you finished chem and bio. So Narcy, do you have any tips for like chem? So guys, you can ask tips. Good, good. So everyone said C5H12. Good job, Pasito, Fahim, Precious, Shakira, C5H12. Congrats, Narcy. Everyone say W Narcy. Okay? Everyone say W Narcy, and guys, you can ask him tips. Or you can ask me tips. C5H12, right? So how did you get C5H12? Because we counted 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But this is isomers. So this is only for N-pentane. We have several different isomers. This is one isomer. So what's an isomer? So who knows another isomer for C5H12? So this one was N-pentane. What if we have a different form? What can we do? This is where we take some creativity. Fahim, we just did mechanisms. We can do that again as well. Which mechanisms do you want to go over? All right. In US, people learning this would be about like what? How old is everyone taking organic chemistry? I think I was 19 when I took organic chemistry. All right, I'm gonna try cyclopentane. So I'm gonna try cyclopentane. If you see cyclo, it means we have a ring. I'm gonna try cyclopentane. So pent. Now this is where we talk about functional groups, kind of. Pent means 5. Ane means we have a cycloalkane here. Ane means we have an alkane. An alkane is carbon bonded to H. And then cyclo means we have a ring. Think about cycle like circle. Hi, Cautious. You're joining on some OChem fun here. Hopefully this is not too scary for you. I know it can be scary. I'm going to bring this down here for cyclopentane. Okay, so I'm going to draw a pentagon here. 1, 2, 3, 4, 5. So low-key, organic chemistry has a lot of shapes in it. So if you're good at shapes, you're going to have a good time with organic chemistry. So now I'm going to draw this in terms of my carbon H structure. This is carbon bonded to carbon here 5 times, because this is what? Cyclopentane. Now I got to see if this is complete octet here. Each of these carbons has 2. Okay, so unfortunately this is not a full isomer. 1, 2, 3, 4, 5. And then we have 2, 4, 6, 8, 10. So why is this not an isomer, chat? This is not an isomer. This is not an isomer for C5H12. Why is this not an isomer? Good. Beep Boop says only 10 hydrogens. Right? Right? Not the same molecular formula. Good. Good job. So we're not going to do pentane. So let's try another isomer. I'm going to draw 1, 2, 3, 4. What if I do this? What if I make a what if I do a butane and then I do this? There we go. What about this one? This is going to be our first. This is going to be iso. So this is going to be 1, 2, 3, 4. This is going to be a 1, 2, 2 methyl. 2. This should be 2 methyl butane, right? So if you need help with naming stuff, here's how you name stuff. I'm going to start by labeling the carbons. 1, 2, 3, 4. And then on my 2, I have a methyl here. This is a methyl. So this is CH3, this is methyl. So that's why I called it 2-methyl butane, because I have 4. But this is also isopentane. Because we had our pentane, this is still going to be 1, 2, 3, 4, 5. So Pasito said sec isobutyl. That's going to be another way of calling this. Sec isobutyl. Sec isobutyl. So this is indeed another isomer, right? Chat, let's do another quick check-in. Let's do another quick check-in. I'm going to ask you guys one question here. Do you want to do more isomers? More isomers, or do you want to go back to mechanisms? Do you want to go back to mechanisms? So that first little ugly figure is supposed to be a happy face. And then if you want to do more isomers, vote for a happy face emoji. If you want to go back to mechanisms, vote for a crying emoji. Fahim says mechanisms, bro. Which mechanisms, chat? Which mechanisms, chat? Guys, pull up the poll is active, 60 seconds on the clock. Make sure you tap the button. Make sure you tap the button or it's not going to register your vote. Make sure you tap the button. I think... Where's the button, chat? I think the button's like somewhere over here. I think the button's like somewhere over here. By the way, anyone that's new here, I'm Dr. Drew. Guys, I got resources for free on my website, link in bio. Go to engineeringminds.co if you want to join the Discord for free. Check out the resources on my website, engineeringminds.co. And if you need tutoring, I got you. I do private tutoring for math, gen chem, organic chem, and physics, and chemical engineering, guys. So just shoot me a DM with the word info if you need more information. Okay, I have lots of free resources on the website, so just sign up for a free call on the website. Hi, Gon. Melanie, thank you for the follow. Gaddy, thank you for the follow. D, thank you for the follow. Guys, how's everyone doing? Comment down below if you're currently in high school or college. If you're in high school, comment high school. If you're in college, comment college. And what is everyone taking right now? What is everyone taking this semester? My background was in chemical engineering, and guys, believe it or not, I struggled so much when I took organic chemistry. Dude, I struggled so much. B-boobs in college. My PhD is in chemical and environmental engineering, bro. Great question. So guys, I just asked the poll, are we going to do mechanisms or isomers? And let's see what we voted for. Let's see what we voted for. Last time we got 4 for isomers. One sec, guys. Let me pull up this poll real quick. Guys, what time should I go live? So we got 5 votes for mechanisms, guys. We're gonna switch to mechanisms. We're gonna switch to mechanisms, and comment down below which mechanism you want to do. Guys, what time should I go live? I usually go live in the evening, but it seems like a lot of people are active now. Maybe I'll go live earlier. Right now it's 2:30 my time. What time is it for you? What time is it for everyone? So I'm gonna do a quick recap of the one that I just did, of my electrophilic aromatic bromination. Studying for admissions test. Good luck. What kind of admissions test are you studying for? Is it for college, university admissions? Oh my gosh, good luck. I'm sure you feel a little bit nervous, but don't be nervous. Feel excited. Don't be nervous. I want you to be excited. You're about to start your journey. Alright. Yes, I've helped people study for the MCAT. I got you for MCAT prep as well. For math, gen chem, ochem, physics. So suppose I react this with BR2. And then FeBr3, chat. So what's this gonna be? What's this product gonna be? So I'm gonna generate a complex. So comment down below if you know what this is gonna be here, or if you have any questions. What would you like to go over? Yeah, I got you for MCAT prep. I'm not sure what's the IMAT. What's the IMAT? I can do basically mathematics, general chemistry, organic chemistry, physics. The only thing I can do, unfortunately, is biochem and stats. Yes, it is. So let's show that. Let's prove that. This complex is going to be formed by creating a complex between the bromium, the bromine, and FeBr3. So there's going to be a plus charge on the bromine and a minus charge here. So if I have a benzene group, this is going to be attracted to the positive charge. Okay? Every time I see an alkene, chat, I think about electronegativity. Every time I see an alkene, this is a high density of electron double bonds here. Okay? Oh, emission test for medicine. Oh, good luck, good luck. Good luck, good luck. So if it has organic chemistry or math or gen chem, I got you. So this is going to be our first reaction here, and then we're going to generate a bromine like this, and then a positive charge down over here. Okay? So we're going to have a positive charge down over here. Okay? So I use that alkene to attack. Every time you see a double bond, chat, just think that it likes to be attracted to positive charges. Then, well, we're almost done actually. We're going to regenerate our bromine Fe minus Br3. And this is going to be attracted to the proton that lives right over here. So this proton is going to get deprotonated and create our final answer, our final product. Okay. Okay. And then finally we have, so if you said this, you're correct. So the people that said a bromine attached to a benzene, just like that, you are good. Okay, perfect. So that's going to be our that. Thank you, Sophia. Thank you, Sophia. I hope this is helpful. Okay. So guys, comment down a thumbs up emoji if that made sense so far. If you're understanding this and you feel you have a good understanding of this mechanism so far, comment down below. Comment a thumbs up emoji. And another common one we can do is nitration. Thank you, Gaddy. Another common one, guys, that's really common is nitration and sulfonation of benzene. So we can go over those next. Except I want you to realize it's going to be more or less the same process. Okay, the only difference between bromination and nitration is instead of a bromine, we're going to have nitric acid in presence of even stronger sulfuric acid. So sometimes people get confused because they get overwhelmed with all the different compounds. But I want you to realize that sulfuric acid here, all this does is reduce the pH. Thank you, Narcy. I missed that. No, you're the GOAT. Thank you. You're the awesome. Thank you for the you're awesome. Thank you, Narcy. I think I missed that. Okay. And then so this is going to be our nitric acid is going to attack that here. And we're going to generate another complex. Let's turn this into HOH N double bond O minus. So this is just a deprotonated. This is just a protonated nitric acid. Okay. Okay. And then carbonyl mechanisms, nucleophilic substitution. Carbonyl mechanisms, nucleophilic substitution. Yeah, perfect. What do you mean, Zaka? Okay, what do you mean by that? So we're gonna use this to generate a nitronium. So let's do it this way. Let's do this way. I'm gonna show the mechanism here between nitrites. I'm gonna show the mechanism between nitrites and sulfuric acid. We're gonna have HOS double bond O, OH, versus our nitric acid HN, HON, double bond O minus. Why does the oxygen have 3 lone pairs? Let me re-show that. It's because it's been deprotonated here. So this oxygen gonna attack this proton right over here. It's deprotonated by this sulfuric acid. Okay. So next, we're gonna generate what? Now in equilibrium, we're gonna have HO and double bond O. This is gonna be a minus charge on the bottom, and the positive charge here and positive charge here. So to establish equilibrium, all we're going to do is remove this water, okay, and create the nitronium ion, which is N double bond O with a positive charge. So the name of this is nitronium. Zach, I'm sorry, I'm not understanding what you're saying here. General is the one. They've learned this? I'm really sorry. So now I'm going to use this nitronium ion. Let me move this down here. I need more space. Okay. And so I'm going to go down here and in equilibrium react with now my nitronium ion, which again was O, double bond N, double bond O. So the person that asked why is it a lone pair? Because it's been deprotonated by the sulfuric acid. The sulfuric acid is a stronger acid than nitric acid, so it deprotonates that nitric acid, HNO2. All right. So now I'm going to undergo electrophilic aromatic substitution. So that means I'm going to take my double bond from one of these. I'm going to take my double bond from, suppose I get it from this one here, and then attack the nitrogen here to create a sort of complex with NO2, just like this. Okay. So that first complex is going to look something like that. And we can undergo resonance. I'm not going to show that right now. I'm not going to show that because it's not necessary now, but I'm going to have NO2 up on here as well as the proton. Positive charge over on this side. Now, remember we generated water. Water over here was generated in this step. So water is H2O, right, chat? Chat, I'm seeing less comments here, so let me know if I lost you. Comment a thumbs up if you're still following along. If you're still following along so far, comment a thumbs up emoji if you're understanding. If you got lost, comment a crying emoji. Don't be shy. If you're saying, hey, I have no idea what you're doing, comment a crying emoji. So what water is going to do... Okay, Fahim says thumbs up. I'm going to continue. What water is going to do, it was generated from this step. We generated water. It popped off the nitronium. Thank you, Rose. Good to see you. Haley, welcome in. So now water is going to be... remember, water has oxygen, has a lone pair. So this is going to function as a weak Lewis base and deprotonate that. And then be left with our final product is nitronium. So the message that I just want to give here, chat, the whole purpose of this was just to show that sulfonation and nitration and bromination and halogenation are effectively the same mechanism. Notice that we have what? For nitration, we have benzene attached to a nitrite. And for bromination, we have benzene attached to a bromine. Guess what? For sulfonation, it's going to be the same idea here, but instead of nitrite, NO2, it's going to be attached to SO3H. Okay? Yes, this is electrophilic aromatic substitution. So, this is effectively addition. Now, this is organic chemistry 2. I think, are you asking, Fahim, are you in OChem 1 or Organic Chem 2? I think this is a little bit more advanced than what you're asking. I think you're asking about addition reactions in general. Please clarify, are you in OChem 1 or 2? Let me go back to nucleophilic reactions. What happens to the water? It gets regenerated, so it's still going to be in the... It's still going to be present. So the water becomes H3O+, but we also have our deprotonated nitrite, HSO3-. So those are going to combine to generate water plus H2SO4. Good question. Okay, those are the same products. You're from the UK. So like electrophilic addition. This one might have been a little bit too advanced for you. So let me go back to electrophilic addition. Addition reactions. Let's do a different mechanism. I'm gonna do an even easier one for you to see, just in case. Yeah, right now doing nucleophilic aromatic substitution. Oh, you learned this? Okay, perfect. So then let's continue. Let's proceed. Let's proceed here with electrophilic, with nucleophilic aromatic substitution. It's called NAS for short. All right. So I'm gonna continue. And then let's do one more. Let's do one more. So I want to show you. No, in US we do this at like 19, age 19. I think you guys are a little bit more advanced. We do this in college. Are you in high school, bro, or college? I learned this in college. So sulfonation of benzene, chat. Let's go ahead and do the same thing. I'm gonna try another benzene. And that's going to be our benzene attached just like that. Okay, so benzene now is going to react with sulfur trioxide, SO3. So sulfur trioxide and concentrated H2SO4. So what happens if I react sulfur trioxide? Let's go down. I'm in what we call year 13, so year before university. Oh, interesting. Okay. So for us, we learned this year 2 in university. So if you're year 13, so then in uni, it's year 1, and then uni, year 2. For us in the United States, this is where you learn this. Hopefully that makes sense. So if you're in the US, you learn it in university in year 2. I think UK is a little bit faster than US. I think UK is like 1 year faster. Because right now we're in uni year 2. Okay? So right now I have sulfur trioxide with concentrated H2SO4. We already saw what happens when we have concentrated H2SO4. This is a strong acid. So strong acid gonna look like this. H bonded to O. Okay, H bonded to O. Bonded to S, double bond O, bonded to O. H. Now, sulfur trioxide is going to look like this. It's our exception for our octet rule. We're going to break the octet rule. Generate this one here. Okay. And then sulfur trioxide is going to function as a weak base and protonate one of the O's here, H's rather, and deprotonate just like that. So we're going to generate a protonated SO3. It's just going to look like this. SOH plus double bond O, and OS double bond O, OH minus. So this is the first step to generate. This is going to be our main function here. We're going to focus on this one. So now I'm going to utilize this one to have this protonated form of SO3. Right, chat? So now I have protonated form SO3. That's going to be my first step here. So I'm going to take what I generated from up above down in this step, chat. I'm going to go down here, SO3. I'm going to go down over here, S double bond O, H plus, double bond O. Okay, so this double bond O, H plus is going to be a positive charge. Namely, we're going to use our alkene here. Alkenes, recall, are negatively charged. So alkene going to be attracted, because it's going to be a negative charge, is attracted to the S down here. And perfect. Now we have our protonated, we have our benzene attached to our sulfur. So we're almost done. We're almost done. The only thing is we have to clean it up. What do I mean by clean it up? I mean I have to attach my SO3. SO3. Let me draw it like this. SOH double bond O. Positive charge lives here now. Okay, I have to clean it up. So now my HSO3 minus is going to effectively, wait, I'm going to draw this as OSO3H minus. So remember, that's from here. Okay, so this one lives right over here. I'm going to highlight this, chat. I don't want to confuse anyone. This is going to be green. Green right over here. That's this green molecule. That's this green molecule. But this one, let's color it orange. From the beginning, first step, beginning step. That's this one here. So now I'm using this one. We'll attack now. Which will attack? Chat, does anyone know which the orange molecule will attack here? I give you a small hint. This orange molecule is going to act as a, is going to function as a weak base. So if it's going to function as a weak base, we're going to effectively take our oxygen here. Attack where, chat? So bases are attracted to protons. So now I'm going to attack this proton. Okay, so this is base attracted to this proton. And then generate. Final answer is benzene. Double bond, just like that. SO3, SO3H. Okay? So this is sulfonation of benzene. Sulfonation of benzene. Very, very similar to the previous two. Nitration of benzene, sulfonation of benzene, and bromination of benzene. We also have halogenation of benzene with Cl2. Okay? Why wouldn't it take the proton from SO3? Why wouldn't it take the proton from SO3? If it took the proton from SO3, great question. Okay, great question, Rose. The carbocation became neutralized to form a double bond. This is addition. This is addition. So addition means we have I'm gonna have X No, we're gonna have elimination. Apologies. There's gonna be elimination. Elimination. Elimination means we're going to remove the double bond. And we're going to have our nucleophile. It's going to be a base, rather. Base is going to be over here. And create a double bond. So the positive charge became a double bond. Just like this. Okay? So this is called elimination. Whenever you see a single bond with a positive charge turning into a double bond, This is called elimination. Now, Rose asked a really good question. Let's address that. So, why didn't it attack this proton here? Good question. Good question. Let me address Rose's question. Rose said, why wouldn't it take the proton from the SO3 here? Suppose we did that. Suppose we did that here. Then we're gonna have SO double bond O minus, which is not as stable. So the reason, Rose, why we didn't attract this H here is because the product is not stable. Suppose we attack this proton instead, then our final product would be something like this. Benzene, okay, double bond. Now we have a positive charge, and we have SO minus, double bond, double bond. So right now, we have a minus charge and a positive charge, but I would prefer if we have neutral. Anything that is neutral is typically more stable because this has a positive charge here and minus charge here. So we're trying to stabilize the carbocation. Remember, positive charge on a carbon is called a carbocation. This is called a carbocation. Okay? Is it always going to break off the water molecules, OH groups, in the beginning of the reaction? No, not always. Not always. In this case, there was no water involved. Not always. This one has no water. No H2O involved. Last time it only happened because we had water in the presence of... we generated water from the HNO3. Is H2O, NO2. So this one broke off water. This is water. H2O, water. Here, there's no water. There's no H2O molecules here. So similar mechanism, but different process here for bromination or sulfonation, okay? Main thing I want you to understand, sulfonation has SO3H, nitration has NO2 attached, okay? And then bromination has Br attached. 3 mechanisms, same idea for bromination, nitration, and sulfonation. Does that make sense? Triple A, welcome in. Okay, I'm gonna stay on for like 5 more minutes. Ask any more like last minute questions. Here's the website if you want to explore the website, Engineering Minds. I'm gonna stay on for 5 more minutes and then I'll come back later, chat. Hello, hello. Gonna stay on for like 5 more minutes. So, guys, this stuff can be complicated, okay? This stuff can be complicated, so don't be scared, okay? Don't be scared. I just want you to study and review the mechanisms. Draw them out from scratch. I'm gonna post this live on YouTube. I'm gonna post this live on my YouTube channel later today, so you can rewatch it and put it on ×2 speed, okay? So for sulfonation, we're generating, the purpose of sulfonation is to generate SO3H bonded to benzene, okay? So the function of SO3H, the function of SO3 attached to H2SO4 was to generate our product. So this is our product here. And so this is going to be a very common test question in organic chemistry. So it has different applications in chemistry and medicine too. I would imagine that this product can be used for medicine as well. I'm not sure what though, but I can look into that if people are curious, okay? The main thing is not to just blindly copy. I want you to practice the mechanisms, draw them out. Like I said, I'm gonna post this on my YouTube channel later today. Okay, great questions, great questions. Okay, so yeah guys, thanks a lot for joining. Thank you for your comments. Thank you for liking the video. We got 1.6k likes. So anyone that's new here, I'm Dr. Drew. And guys, here's the free resources you can download. Let me know what you would like to see next. You can shoot me a DM. Thank you, Fahim. And yeah, hit that follow button. Good to see you. Good to see you. And yeah, guys, so if you're taking like organic chemistry, you can join the Discord. You can explore the resources. All of this is free, by the way. But if you need tutoring, I got you for tutoring as well for math, gen chem, ochem, physics. Thank you for the follow. Welcome in. And guys, the Discord's free. So if you want to join the Discord, just tap that link in bio and then click join here. And there's about over 300 members, almost 400 people in the Discord. You can ask questions, you can interact with people, and share any tips or ask any questions for chemistry. Okay, just a quick little live today. I will be back later today if you're still awake. I'm gonna be back in about 2 or 3 hours. All right, guys, I'm gonna end the live stream for now, but I'll post it on my YouTube channel later today. Thank you, everybody. Have a great rest of your afternoon or your night. Thank you. Have a good night.